Welcome back to Phys 3500 at the University of Windsor. I'm your instructor, Dr. TJ Hammond. On Friday, September 25th, we'll be continuing to discuss calculus of variations. We'll be finishing up this chapter, this lecture. So why are we covering this? Why are we covering calculus of variations? So as I said before, up to now, classical mechanics has been formulated for you by Newton's laws. So in Newton's laws, of course, we have that the rate of change of the momentum is given by some force, or F in general. F is equal to d by dt of p. And you're probably, you know this more likely as F equals ma. But it turns out that you can actually formulate mechanics based on energies and scalars instead, and so those are with Lagrangian and Hamiltonian mechanics, where the energies dictate particle trajectories rather than forces and momenta. We'll finish up this week talking about when we have constraints on the motion, and that'll introduce us to the concept of Lagrange multipliers. And this will be basically the end of the concepts, these kind of abstract concepts that you'll need to understand how to approach Lagrangian and Hamiltonian mechanics. So for this daily assignment that's due Monday, I want you to think about what we've learned this chapter on calculus of variations, reflect back on that, think about what you've learned this week, think about what makes sense, how you can approach these problems from this generalized sense of taking an extremum of this, this functional, but also what doesn't make sense. Do you still not have that much intuition? You probably have a lot of intuition with Newtonian mechanics, but you might still not have that much intuition with how to approach these problems. So, you have Euler's equation, but maybe you still don't exactly know how to set up Euler's equation or something like that. So let me know. Okay, so to remind you, what we end up with is, in order to have this functional j to have an extremum, we end up with Euler's equation, and that is the partial derivative of f with respect to y, which is our independent or our dependent variable, minus the derivative, the full derivative with respect to our independent variable of the partial derivative of f with respect to y prime, which is the first derivative of our dependent variable, and that equals 0. So this is Euler's equation in the first form. This is a necessary condition for j, this functional, to have an extremum. So we don't actually need to solve for j, this whole thing. We just need to know that j has what causes j to have that extremum, and that is given by this Euler's equation. So we did some examples earlier on in the week on how to use Euler's equation, but now we also have Euler's equation of the second form. So when the function, this function f, doesn't explicitly depend on x, then this first derivative of f with respect to x, the independent variable, if that's equal to 0, then we get Euler's equation in the second form, and that's written as the partial derivative of f with respect to x, but of course we know that's going to be 0, minus the full derivative with respect to the independent variable x of f minus y prime over the partial derivative of f with respect to y prime. And that's equal to 0. But since that the second term is now going to be equal to 0, since that's a derivative of something is going to be equal to 0, then that means that that something is actually a constant. And so that is Euler's equation in the second form, is that f minus y prime df by dy prime is equal to some constant. Okay, so we will use this for an example. So we'll be covering this concept of a geodesic. So this will also be important to your homework assignment. But basically, if you've ever seen a flight going from Hong Kong to San Francisco or Hong Kong to LAX or something like that, and you see these big looping trajectories as they're plotted on a Mercator map. If you've never really understood how this happens, well, you have to think about how these projections actually look on a globe, and it turns out the shortest point from one side of the globe to the other is actually a straight line, but it's a straight line constrained by going on the surface of this globe. And so if you actually plot this globe as the sphere here, the straight line would be some kind of arc that's going from point A to point B, but it's a straight line, but it just goes around this globe. And so that's why these projections end up having these kind of really weird shapes, especially if you go from something in the southern hemisphere to the northern hemisphere. So in class, we'll be solving this example. To finish up, we'll be talking about Lagrange multipliers. So this is when Euler's equation has a constraint. So if we add some constraint, g, which is a function of y, the dependent variable, and x, the independent variable, then we need to incorporate this into Euler's equation. How we incorporate this is by adding an undetermined multiplier to the constraint. So Euler's equation before was, of course, di f by di y minus d by dx di f by dy prime, and that's equal to 0. All you have to do now is recognize that you're adding in this constraint, which is, as I said, it's going to be dependent on y, so we'll have di g by di y, but we multiply it by this, this unknown multiplier, this Lagrange multiplier. And then we set that equal to 0, and then we solve for that equation, and that is what we need to do. And in class, we will be going through several examples of this, so we'll be starting with this Dido problem. And then we'll be going through more examples to finish up this lecture, and that will be it for the week. And then we go and we use these new tools, this new kind of abstract mathematical concept that we've developed, and we'll be applying that to potentials, and will be giving us equations of motion, just like what we would get from Newton's laws. All right, so that's it for this week on calculus of variations. Looking forward to see you in class.